So, welcome to today's webinar. I am Shilla Nawaz, and it is my pleasure to introduce our esteemed speaker for today's session. Please join me in welcoming Engineer Kaffayatullah Khan. Engineer Kaffayatullah Khan is a distinguished professional engineer with over 15 years of experience in teaching and research, specializing in construction and building materials. His work primarily focuses on sustainable building materials, innovative decarbonization technologies, life cycle assessment, and the performance evaluation of high and ultra-high performance green concrete. He has made significant contributions to the field through numerous high-impact research articles and patents. His exceptional achievements have earned him recognition among the world's top 2% of scientists in the domain of construction and building materials, as per the prestigious list published by Stanford University. Throughout his career, Engineer Kaffayatullah Khan has successfully bridged the gap between academic research and practical implementation. He has fostered collaboration with both academia and industry to develop solutions for real-world challenges. His commitment to sharing knowledge, driving innovation, and advancing sustainable and efficient construction practices is truly inspiring. Thank you, sir. I will now hand it over to you. You can start.
Can you hear me?
Yes, sir.
Thank you. Bismillah ar-Rahman ar-Rahim. My name is Kaffayatullah Khan. I'm a senior faculty lecturer in the Department of Civil and Environmental Engineering, College of Engineering, King Faisal University. It's an honor for me to be with you in this webinar, and I welcome all of you in this talk. So the title of today's webinar is Environmental Impacts and Decarbonization Strategies in the Cement and Concrete Industry. So the main content of today's talk will be the use and importance of concrete. We will talk about the future demands and the associated issues with the cement and concrete. And we will talk about the roadmap to net zero emissions, and finally the environmental impact of concrete. Then we will talk in detail about the decarbonization strategies in the cement and concrete industry, and clinker substitution with supplementary cementitious material in concrete. And we will also talk about the carbon capture, utilization, and storage. And finally, there will be a question answer session, and I would love to get questions from all of you. So let's talk about the concrete. How important is concrete for our planet? So concrete is the most abundantly used material in the world, next to water. So after water, the most consumed material in the world is what? Is concrete. So around 25 to 30 billion ton of concrete is used annually around the globe. So this means that 4 metric ton of concrete for every person on this earth. And the most important ingredient of concrete is cement, whose annual production is around 4.2 billion ton, according to 2019. So there are some very good reasons regarding the massive use of concrete. So one of them is that it is very economical. So compared to all other construction material, it is the most economical material for construction. And it's versatile. Concrete can be used for many different applications. And it is highly durable compared to other material like steel, wood. It is very durable. And it is easy to construct. And the most important thing is that the raw ingredients which is available, which is required for the production of the concrete, is available everywhere in the world. And finally, we can construct a very beautiful buildings and infrastructure with the help of concrete. So you can see the simple example is the Dubai. So the beauty of Dubai is because of the concrete. It's a desert. There is no natural beauty, but Dubai is beautiful because of the concrete. So now we will talk about the future demands of the concrete. So according to the estimates, by 2060, the world is projected to add 230 billion square meter of buildings. So what does this mean? This means that doubling the entire current global building stock. And this is, according to the estimate, this is also equivalent of adding an entire New York City to the planet every 34 days for the next 40 years. And the reason for such a massive demand of the concrete is the rapid increase in the population and urbanization. So now we will talk about the environmental impact of the concrete. So overall, cement and concrete industry is responsible for 8 to 10% of the total global carbon emissions. And these emissions are causing global warming and climate changes, which have serious consequences for human and natural ecosystem, like in the form of fires, drought, floods. This is all because of the global warming and climate changes. So according to Paris Agreement of 2015, the world community pledged to reduce the global temperature of the world to below 2 degrees centigrade and to keep it to 1.5 degrees centigrade above the pre-industrial levels by 2050. So this is the target, that we have to keep the global temperature below 1.5 degree. The problem is that these emissions are causing actually global warming. They are increasing the temperature of the earth. So that's why we have to keep the temperature by 1.5 degree by 2050. So International Environmental Agency have introduced a net zero roadmap. So this is actually a global pathway to keep the earth temperature within the limit of 1.5 degree. So according to IEA study, achieving the target of around 50% reduction in the global emissions by 2030 in the concrete industry, it would require to reduce 18% of the cement emissions. So compared to 2006 baseline. So in order to achieve the 2050 target, so there is a very popular challenge which is called Architecture 2030 Challenge. So what is Architecture 2030 Challenge? The Architecture 2030 Challenge is that until now, the carbon emission is reduced by 40%. By 2025, we have to reduce by 45%. And by 2030, we have to reduce the carbon emission by 65%. And eventually, we have to make it zero emissions by 2040 in the cement and concrete industry. So this is the Architecture 2030. Also, the Global Cement and Concrete Association have also a roadmap for net zero concrete by 2050. So according to that roadmap, so we have already, like, some of the carbon emission have been reduced by adopting different technologies. But the most important decade is that between 2020 to 2030, we have to reduce significantly. And eventually, we have to achieve the net zero target between 2030 to 2050. So before talking about the strategies which is required to reduce the carbon emission in the cement and concrete industry, so we will first talk about the understanding carbon for building sector. So actually there is two type of carbon uh, associated to the building sector. One is called embodied carbon and the other is called operational carbon. So in embodied carbon is actually the carbon which is associated with the manufacturing, transportation, and installation of the construction materials. So it starts from the manufacturing of the raw material, transportation of the raw material, and finally the installation of these raw materials like concrete in the form of constructing a building, roads, dams, etc. So these type of emissions are called embodied emissions, which are associated with the materials. And there is operational carbon. So actually these carbons are actually related to the building energy consumption. So the consumption after the construction of the building, the emission which is linked with that is called operational carbon. So according to studies, it is expected that by 2050, 90% of the carbon associated with the building sector will be related to building materials. So 90% of the carbon will be embodied carbon and only 10% of the carbon will be operational carbon. So this is the target, because a lot of low carbon energies technologies are introduced the for the building operations. So we have to work to reduce the embodied environmental impact of the material which is used for the construction of the buildings. So this graph actually show the embodied energy and embodied carbon associated with different construction materials. So you can see in this graph, there is different materials: steel, glass, plastic, bitumen, concrete, cement. So you can see this graph show that concrete have very low carbon and energy impact. But the problem is the massive use of the concrete. So compared to steel and other materials, concrete use is very massive. We have already discussed it's 20 to 30 billion ton. So that's why its overall impact is very huge. So you can see the carbon emissions from the different processes during the production of the concrete. You can see there is a carbon emission associated with the mining of raw material, which is used for the manufacturing of cement. And during cement manufacturing, huge amount of carbon emissions release. Then the transportation of these materials to the concrete mixing plant, and the concrete production have some carbon emissions. Then the transportation of the concrete to the construction site. And then there is one phase where concrete take carbon from the air. So during its use phase. So that is it. And also, if after the demolishing of the structure, if we reuse the material, the construction material, so we can get some carbon back. So this is the whole process of the use of the concrete and the carbon impact, the associated carbon impact. So this graph, actually on the left side, you can see what is the percentage of different ingredient by mass. You can see cement is only 13% by the mass of the concrete. And on the right side, you can see the carbon emission associated with the different ingredient of the concrete. So you can see 79% of the carbon is associated with cement only. and the remaining 20% is with the rest of the material. So cement is the more carbon intensive material in the concrete. So now we will talk about the decarbonization strategies in cement and concrete industry. So you can see there are basically 4 major strategies which can be used to reduce the embodied carbon impact of cement and the concrete. So the first one is the innovative technologies which include carbon capture, storage and utilization. The second one is the reduction of clinker to cement. The third one is the fuel switching. And finally, the fourth one is the thermal energy efficiency and electric intensity. So the first technology, which is the carbon capture, storage and utilization, it can reduce the carbon emission by 56%. The clinker reduction, by replacing it with the cementitious supplementary cementitious material, it can reduce the carbon emission by 37%. The fuel switching means that you can use renewable energy sources instead of coal or crude oils. So if we switch the fuel with the more renewable options, so we can reduce up to 15%. And finally, by optimizing the thermal efficiency of the kiln, cement kiln, and electric intensity, we can reduce 10% of the carbon. So the 2 most important strategies are actually the carbon capture and the clinker substitution by some supplementary cementitious material. So I will talk about these 2 technologies in detail. So first of all, I will talk about the clinker substitution with supplementary cementitious material. So there are many binders which can be used as a supplementary cementitious material by different percentages in the concrete. So the composition, the performance and availability of these materials actually varies significantly. So you can see Portland cement is the most commonly used material for the production of the concrete. We have natural pozzolan like volcanic ash, volcanic pumice, zeolite. These material have potential to replace cement by some percentage. There is a calcined clay. Calcined clay is when you heat the kaolinite clay at some high temperatures, so it become amorphous and it can be used as a SCM in the concrete. Then the most popular one is the fly ash, which is the byproduct of coal thermal plant. We have granulated slag, blast furnace slag. This is the byproduct of the steel industry. And there is a glass. If we grind the glass, make it powder, we can also use it as a supplementary cementitious material. And there are so many other materials, the agricultural waste, and there is so many other industrial waste. It can be used as a binder, especially as a cement replacement in the concrete. So the problem is that clinker is producing a lot of emissions. So if we replace clinker by some percentage with those materials which have low embodied carbon, so actually we are reducing the emissions of the concrete. So now the problem is the availability and the use of these supplementary cementitious material. So you can see, compared to Portland cement, the available supplementary cementitious material quantities are very less. So you can see the silica fume, it's very small. Then we have some vegetable ashes, we have some natural pozzolans, slag and fly ash. So all these material, they are currently in use by some percentages as a replacement of cement. We have 2 new materials nowadays which is more commonly used. One is the filler. Actually, it is the limestone, powdered limestone. It is used as a filler by 10 to 15%. And then we have the calcined clay, which is available in huge quantity everywhere in the world. So this is the most potential material which can be used as a replacement of up to 50%. We can use this material as a replacement of cement. So actually today, on average, only around 20% of SCMs are used as a substitute to Portland cement in the concrete. And there is actually a problem associated with the most popular slag and fly ash, which is the availability of adequate quality uh, of fly ash and GGBS is now limited. And there is also supply and demand issue associated because of the global shift from coal thermal plants to renewable energy resources, and also from ground granulated blast furnace slags to electric arc furnace slag. Because of this shift, there is issue with the supply and demand of both fly ash and GGBS. And there is another issue. Actually, in most of the concrete application, and especially the high performance application, there is a limit on the clinker substitution, and which is associated with the adequate strength gain at early age. So if we replace these pozzolan at high percentages, so there will be a problem in the early age strength of the concrete, and which is required in some cases. Otherwise, it will delay the construction timelines, and there will be other issues also. So most of the available SEMs, the conventional SEM, which is fly ash, rice ash, volcanic ash, they are non-hydraulic and moderately reactive. So it is causing significant reduction in the early age strength when substituted at high levels. So the target is to replace cement by 50%. This is the target in order to achieve the IA roadmap. So you can see the calcined clay, which is also called metacoline. The commercial name of this material is metacoline. And limestone calcined clay cement, this is another type of cement which is called LC3, are best fit for replacing 50% of the cement and also maintaining better performance. And there is another option, which is the coupled SCM system. What is this? It is a combination of conventional SCMs, which is moderately reactive, with highly reactive SCM like metacoline, micro, and nanosilica. So if we use these together, so we can replace the clinker by high amount up to 50% without compromising on the strength and durability performance. So the promising technology of coupled SEM system would pave the path for high clinker substitution and ultimately result in the development of stronger, sustainable, and long-lasting concrete. Another option is the high strength concrete. So if we use high and ultra high strength concrete for our application, so there is a benefit. The benefit is that if concrete is stronger, less of it will be needed. So we will need less material. So, and also it will be more durable. So if it is more durable, the structure will last longer. So using high strength concrete grades, we can reduce the overall consumption of the material. And in case of high strength concrete, so there will be a lower steel quantity required. So ultimately, the overall embodied carbon impact of our structure will be reduced. So now I will talk about the more innovative technology, which is called carbon capture, utilization, and storage. This technology is very innovative. There is a lot of research nowadays going on, but still it's not very developed and it's very costly. So we will talk about this technology. What is this technology and how it will reduce the carbon emissions in future. So carbon capture, utilization, and storage refers to strategies that incorporate or utilize carbon dioxide in the concrete production process, either to reduce its carbon footprint or enhance the properties of the final product. So this can be done through carbon curing methods and development of carbonated concrete. So the key concept regarding carbon addition and curing in concrete are discussed in this slide. So first of all, we can use carbon for curing purpose. So the carbon which is actually emitting from the cement plant or any industry, if we capture those carbon and then utilize that carbon for curing purpose. So instead of water curing, if we cure our concrete with in carbon environment, so this is called basically carbonated curing, and this is also called enforced curing. So carbonated curing is a method in which carbon dioxide is intentionally added to the curing process of the concrete. So we will cure our concrete in carbon environment. So what will happen when we cure our concrete under carbon environment? So when concrete is exposed to the carbon during curing, a chemical reaction occur between CO2 and the calcium hydroxide, which is one of the major product of hydration reaction in the concrete. So what will happen when carbon will react with calcium hydroxide? So calcium carbonate will form, and this is very stable compound, and it will increase the initial strength of the concrete because of the formation of calcium carbonate. So what are the benefits of carbonation curing? So it will enhance the early age strength. So if we compare the concrete cured under carbon environment and under water, so the 1 day strength of the concrete cured or under carbon environment will be more than the water cured concrete. So this is because of this carbonation reaction and the formation of CaCO3. The second benefit is that carbon dioxide will be we can sequester carbon dioxide in the concrete. So carbon will be absorbed by the concrete and it will be there over its lifetime. So carbon will be there. So one of the major issue nowadays is that how to store the carbon. So we can easily store carbon by this method in the concrete. So it will be there until concrete is there. So if we break the concrete and reuse it, then carbon maybe it can be emitted again, but when the concrete is there, so carbon will be there in the concrete. Also, another benefit is the speeding up of production. So carbon curing can accelerate the curing time, so allowing the faster production cycle, which is particularly useful for precast element. So in precast, like block and other panels, so we can reduce the curing time by using this technique. And also the energy saving. So normally in the precast industry, high temperature curing is used. So instead of using high temperature curing, so if we use this carbon curing, so we can reduce a lot of energy consumption by this way. So now another way of utilizing carbon in the concrete is by adding carbon into the concrete mix during mixing phase. So carbon dioxide can be introduced during the mixing of the concrete in small amount. The amount is very small, 0.2 to 0.5%. It depends on the type of the concrete. So what will happen? This carbon will react with the calcium which is present in the cement, and it will ultimately form again the calcium carbonate. So this method will help to bind some of the carbon within the concrete itself, and it will also reduce the emission because you are utilizing the carbon, and it will also give you slightly higher strength. So we can also reduce some of the cement amount uh, from the concrete, and there will be no compromise on the strength gain. So we can reduce the amount of cement by this method by some percentage, like 5 to 10% we can reduce the amount of cement, and we can get the same strength. So now what are the challenges and considerations? So there is a lot of challenges in adopting this technology, especially this carbon capturing, utilization, and storage. So some of the challenges are carbonation limit. So the carbonation process can only penetrate a certain depth. So if we cured our concrete in the curing environment, so this carbon can penetrate up to certain depth. So this will be then there will be a limitation on its effectiveness in the large structures. So this is one of the limitation. The second limitation is the control of carbon in curing. So ensuring that the right amount of carbon dioxide is introduced at the correct temperature and pressure during curing is critical for maximizing the benefit. So overexposure or insufficient carbon could uh, lead to negative results. So that's why it is very important to optimize the carbon amount, the temperature, and the pressures at which this carbon can be inserted or it can be used for curing purpose. So this is very important to optimize all these parameters when carbon is used as a curing agent. And finally, the long-term performance. While carbonation can enhance concrete properties, excessive carbonation can lead to the weakening of the material in extreme cases. So what will happen actually if we add more carbon? So what will happen? CaOH2 will be utilized, and this CaOH2 is responsible for the high pH of the concrete, and this high pH actually help in protecting the steel reinforcement from the corrosion. So if more CaOH2 is utilized because of carbon curing or carbon addition, so pH of the concrete will be low and your concrete will be exposed to corrosion. So that's why it is very important to evaluate the long-term performance of both these technique so that there should be no corrosion related issues with steel reinforcement. So example of carbon addition and curing innovation. So there is a lot of companies nowadays, they are working on these technologies. The most popular one is the most famous company is the Carbon Cure. So what they are doing, they are utilizing carbon. They are injecting carbon inside the concrete mix. So they are actually using this carbon in the ready mix industry. And there is a carbon clean technology. There is another company they have a lot of pilot projects that are focusing on utilizing carbon to produce carbonated concrete blocks and precast elements. And also Saudi Aramco, they are also working on some pilot projects focus on carbon curing of concrete blocks and precast elements. And also there is a company which is called Solidia Technologies. This is US based company. They have actually developed a cement which is called Solidia cement. And this cement actually react with carbon dioxide in the presence of moisture and only need 1 day curing. So the specialty of this cement is that it doesn't react with water, it reacts with carbon, and to get the maximum strength, it just need 1 day curing. And the performance of the concrete is much better than the conventional concrete. So this is their product, patented product, and they are now, it is available in the market. So the conclusion and the final remarks about the different technologies which can be used to reduce the overall environmental impact of cement and concrete is that according to IEA, International Environmental Agency roadmap, so among the 4 different strategies, the most important, practical, well-established, and conveniently implementable to the ready-mix industry is actually the clinker reduction by introducing emerging SCMs. So this is the most easily implementable way to reduce the carbon emission from the cement and concrete industry. And the second thing is the optimize and the effective utilization of cement in concrete production. So according to IEA, these 2 areas have significant potential for reducing cement industry carbon emissions in the next 20 to 30 years. So these 2 technologies can play a very important role in the next 20-30 years to reduce the carbon emission from the cement and concrete industry. The problem with the carbon capturing, storage, and utilization technology is that it is very expensive and not yet developed. So once it is developed and if it is economical, so the impact of this technology will be huge, but still a lot of research is required to further make this technology economical and optimized. So these are some of the references for the information which I shared in this presentation. And thank you very much for listening. So if you have any question, I would love to get question from you people. So please. So the question they can write in the chat box or they can ask directly. So one of the question from Mohammed Farhan is what to do with the already released carbon emissions. So there is a lot of now there is a lot of technologies, a lot of research going on how to capture the carbon from the air. So they are already working on these. So the target is actually, as I told you, the IEA target is to not increase the earth temperature by 1.5 degree. So the issue is with the future emissions. The emission which is already done, it is done. So scientists are already working on like different technologies, how to capture the already emitted carbon from the air. So they are already working. But the important thing is that we should reduce the future carbon emissions from different industries. Yeah, so the Paris Agreement, yeah, so the Murad Ali Khan is asking about the Paris Agreement. So the Paris, in Paris, the world community, they united and they pledge to reduce the carbon emissions from every industry so that we can reduce, we can keep the earth temperature up to 1.5 degree by 2050. Actually, what happened? So let me explain. Actually, what is the role of these carbon emissions on the earth temperature? Actually, when these emissions goes to the air, so these carbon dioxide and methane and nitrogen oxide, these are the different gases. So these gases actually absorb energy, heat. So it keep this heat within itself for certain period of time. For different gases, there is a different duration. So if more emissions will occur, so more heat will be absorbed, and ultimately it will cause an increase in the earth temperature. So this was in Paris Agreement, they decided to limit the carbon emission from every industry. So every country have to contribute to this so that the earth temperature should not increase by 1.5 degree because of these emissions. So this is the Paris Agreement. So the next question is from Javed Islam. How can we adopt our cement industry to utilize SCM? Yes. So in Pakistan, I don't know. They I think they are not using any supplementary cementitious material. They are not producing blended cement uh, because maybe they are not familiar with these options. There is so many option available in Pakistan. There is a lot of reserves of calcined clay and natural pozzolans and industrial byproducts, which can easily be used to produce blended cement. But cement factories, they are not utilizing these things in Pakistan. In Saudi Arabia, there are some cement companies, they are producing green cement by adding 20% of natural pozzolans. Recently, they made one contract with one European company to produce calcined clay cement. So they are already working on this. So there is a lot of options, and globally, the cement industry have already adopted those options. So there is a need of awareness, and the government should implement these policies so that cement industry, cement manufacturers should go for green cements rather than the conventional cement. So how to calculate the carbon emission in the construction industry? So there is actually a lot of tools. They are available. Green concrete tool, and there is a lot of other. There is many tools. They are available, and with the help of those tools, you can measure the embodied carbon impact of your materials, whether it is concrete, whether it is steel, and you can measure for the whole like project, whether it is building roads. So with the help of those software, you can measure the carbon emissions associated with your projects. Yes, these are the innovative cements. Magnesia. There is a question from Farhan. Can we say these will be magnesia and calcium-based cements, which will obviously need more research? There is no proper mix design for that. Yeah, still this is in the initial stages. So a lot of research is going on developing different type of cement rather than the conventional cement. The problem with the conventional cement is basically the calcium carbonate. 60% of cement is made of calcium carbonate. So what happened when we heat the cement? So the carbon dioxide from calcium carbonate it emit. So that's why the conventional cement have huge embodied environmental impact. So 1 ton of cement actually produce 1 ton carbon dioxide. So if we replace the conventional cement with the other type of cement, so definitely we can reduce the carbon emission associated with those cements. So very good questions. So can you please, if you have some more questions? Is the low carbon concrete expensive? It depends on the material which you are using. Like if most like mostly the low carbon concretes, they are cheap. Uh, but it depends on the availability of the material, its processing cost, and all these things. So ultimately, like if you use like locally available material, so ultimately your concrete will be low cost and also it will be sustainable. But if you are dependent on imported materials, so of course that will be expensive, and uh, it will be your concrete will be sustainable, but it will be expensive. So there is a need that the available like SCMs, locally available SCMs should be explored and its performance should be examined. So, so that we can use the locally available SCMs to get cheaper and sustainable concrete. Yes, Mohammad Farhan, what is this? Farhan, carbon clock? So regarding any database of material available in Pakistan, so I don't know about the database of these material, but uh, I have some information regarding some of the material which is available like clay. So you can see a lot of clay resources are available in Pakistan in different area, and also the volcanic ashes and volcanic pumice, these are also available in different parts. So these materials can be used as a supplementary cementitious material in the concrete. So Mohammad Farhan is asking about the geopolymer concrete. Uh, the problem with the geopolymer concrete, it is called zero cement concrete because we are not using cement in this concrete. Geopolymer is basically actually we use this supplementary cementitious material uh, and we use some alkalines to activate these supplementary cementitious material, and it will act as a binder. So the problem with the geopolymer concrete is actually it is not suitable for the ready mix concrete to adopt this type of concrete in their plants. So the availability of raw material is one of the issue. The availability of this alkali activators, this is the issue. So there are some challenges associated with this type of concrete. But in some countries like Australia, they already they made one airport and some high-rise building with the help of this geopolymer concrete. So this can be a replacement for the conventional concrete, but there are still some issues, and especially cost is also one of the issue, availability of the material, and adaptability of current batching plants to this type of concrete. This is the issue. So Mr. Tariq is asking about the carbon. Can we divide the carbon into carbon and oxygen? So I don't know about this. This is not my area. So maybe the expert in this area can answer this question. That is there any possibility to divide the carbon and get the oxygen from it and use it for some other purpose? So I have no idea about this. Yes, any other question? Thank you, Farhan, for asking very good question. So actually net zero emission means that the overall actually emissions related to the production of the concrete is zero. So practically, this is not possible to get net zero emissions, but theoretically you can say it is net zero. Let's suppose like there will be, especially there will be emission from the cement plant, but if you use these emissions again, if you store it or use it for the production of the concrete, so ultimately the overall carbon emission which is associated with the concrete industry, you can say that it is zero. Otherwise, net zero is theoretical term used. Practically, it is uh, not possible to make it net zero, to make it like carbon free. So low carbon building or green building. So this is same thing. The main thing is that the carbon emission which is related to our buildings, it should be low. If it is low, then it can be called low carbon buildings or green building. So if you are reducing the carbon emission related to your building, so means you are going to all, you are making it green. So these terms is used. Sometimes people use green concrete, green building, sometimes use low carbon building. Pure cement, zero cement concrete is possible in the future. No, actually we are not sidelining. Actually, we are not sidelining. This, what we are doing, we are shifting toward zero carbon or low carbon industry. So I don't know, in the near future, there is no possibility to make the use of cement, like to make it zero. There is no possibility. Even by 2050, there is no possibility. But scientists are working on different other technologies, so we can actually minimize the use of cement. So the pressure on the our like building and infrastructure energy industry is so big that we cannot avoid the role of cement. So cement will be critical for fulfilling the infrastructural needs, but we can reduce the amount of cement in the concrete. So I don't understand your question. We can use this green concrete as a sibling or supporting material. Which type of concrete you are talking about? So what is the progress of KSA construction industry? Will they achieve the net zero target by 2050? They are trying their best. So I can see very good progress in the last few years regarding the low carbon technologies in the construction industry, especially like regarding concrete. As I told you, they are already producing blended cement by adding 20% of pozzolan, and they are also working on this carbon cured concrete, and they are also introducing the calcined clay cement. So they are working on this, and hopefully there is a possibility uh, that they will achieve the net zero target by 2060. So Saudi Arabia have a vision of achieving net zero by 2060. So they are already on track. Yes, so what are the innovation in the KSA industries? So actually they are working on even 3D printing also. I know about many collaboration between the 3D printing companies and government organization here in KSA, and different companies, they are working on this. So they are in every area, they are working on actually producing green cement. They are working on recycling technologies. So in many industries, they are working on introducing like green technologies so that the overall like the emissions from different industry can be reduced. So my major research area is actually developing green cement and concrete uh, materials. Especially I'm working on developing uh, low carbon, high performance and ultra high performance concrete, evaluating their performances, mechanical and durability performances, microstructural assessment, life cycle assessment of the concrete, and also we are using the machine learning techniques to optimize the performance and mixed proportion of the concrete. So these are actually my areas of research. Yeah, there is a regulation, there is a codes. ACI have recently introduced a low carbon concrete code. So already they have introduced. So Saudi Arabia is also working on this. So in future, there is a possibility that they will also uh, add those codes and will implement. Yes, I will share my email. Just let me see my email. I will write here. So this is my email. So anybody can contact me. This is my personal email and this is my KFU email. So I am open to any type of collaboration in the area of like cement and concrete. So if you need any help, any assistance, uh, I'm ready anytime. You can contact me by email. Uh, I would like to help students in different part of the world uh, in uh, supervising their like research, thesis, anything. So if we work together, so we can ultimately we can reduce the environmental impact of cement and concrete industry, and we can save our earth. Because this global warming and climate changes, this is causing huge destruction. Uh, in Pakistan, we have seen a lot of floods uh, and lot of rains, unexpected rains, fogs. So this is actually because of this climate changes and global warming. So this is our responsibility to work together and reduce the carbon uh, emissions related with different industry. So construction and concrete industry is our area. So we should work in this area to reduce its environmental impact. Yeah, so definitely uh, they will share the recording, and it was like just 1 hour session. So um, Mr. Rahmat Hakim, so you can also contact me anytime by my email if you need anybody need any help, any guidance. So I'm ready anytime. uh, so thank you very much for attending this webinar, and thank you very much for your questions. It, the questions were great, very knowledgeable questions. So most welcome anytime, inshallah. We will meet again. Hopefully, I will also arrange one more seminar in the future, webinar regarding the life cycle assessment of concrete. How to measure the life cycle assessment of the concrete. So there was some questions regarding this. So I can give you like some case studies regarding how to measure the environmental impact assessment of cement and concrete. Yes, you can, Samiola, you can get the recording of this lecture. So thank you very much. If there is no question, so I think it's time to conclude today's webinar. So, dear participants, thank you very much. So I think now it's time to finish this webinar. Thank you again for attending. Assalamu alaikum wa rahmatullah and goodbye.